Let's solve this system of linear equations using an augmented 2 by 3 matrix. Okay, remember that in matrices, we are going to perform elementary row operations to each of the equations. So sometimes these are known as 3 single elementary row operations because we could only do one of these at a time. So what are they? Well, we could interchange any 2 rows. So we could switch the ith row with the jth row. We could scalar multiply a single row and store it in that row. We could also scalar multiply a single row and add it to another row. And then we store it in the second row that was mentioned. The general strategy for a 2 by 3 matrix is we want to first have this leading 1 in the upper left-hand corner, and then followed by a 0 right below it. And the way we're going to get these 1s and 0s is to perform elementary row operations at the right time. The third part of the strategy is get a 1 in that second row at that very specific position, and then we'll work our way back to get our 0 in the first row in that position. Okay, so recap. First thing in the strategy is the leading 1 in the upper left-hand corner. Another hidden strategy is try to avoid adding fractions. Try to avoid this as much as possible. Okay, only introduce adding fractions when you absolutely have to. The other thing you want to remember about elementary row operations is we will never subtract in our procedure. We'll always add. So let's go ahead and get started. Let's draw our matrix with a bracket. 4, 8, negative 16 are the numbers that represent our first equation. Augmented here is augmented meaning separation. So we're going to draw a separation bar right there to separate the 8 and the 16. So let's draw that separation bar. So wherever the equal signs were, there's now a bar there. Now, the second equation is represented by negative 8, negative 14, and 32. So, how do we get that leading 1 in the upper left-hand corner? We're going to do 1/4 times row 1 and store it in row 1. Notice that changes the first row, but the second row does not change whatsoever. Now our goal is to get a 0 in that second row right below the 1. So we're going to do 8 times row 1, add it to row 2. We now store in row 2. This is now row equivalent to 1, 2, negative 4, 0. We got a 2, and then we got a 0 again. Now we're on step 3 of our strategy. We want a 1/2 times row 2. We store in row 2. That means I'm going to keep row 1 the same. And finally, we have one more step to go. So let's try negative 2 times row 2, add it to row 1, and we store in row 1. Notice I like to work down with matrices. So we work down and try to make things as neat as possible. This symbol here is actually meaning row equivalent. So that's not an equal symbol. Make sure you write tilde, which in this case means row equivalent. So row 2 doesn't change. So a good habit to do is to actually recopy the row that won't change. That way you don't make so many mistakes. And then we have negative 4. The key with reading matrices is that actually we read it from the bottom all the way up. So to complete the Gauss-Jordan elimination, we actually read this from the bottom row all the way up. So the bottom row says that y is equal to 0. I should make that a little bit neater. Right here, y is equal to 0, and then x is now equal to -4. Of course, when we write our solution, we can put it in a set, and this set will consist a unique solution or a unique ordered pair. Okay, so we have a set containing a unique solution to the system of linear equations.